An architect with a daring vision. A vision he will have to fight for. The Bahrain World Trade Center rises on the shores of the Persian Gulf. What makes this building unique is not its height or beauty, but its green technology. It will be the first skyscraper in the world to be powered, in part, by its own wind energy. In theory, it's a brilliant idea, but nothing like this has ever been attempted. With the Earth's temperature on the rise and the need for clean energy greater than ever before, the stakes for the Bahrain World Trade Center couldn't be higher. For decades, wind has led as the planet's #1 source of clean energy. Wind turbines worldwide have the capacity to produce 74,000 megawatts, which could power at least 20 million average US homes. Almost all this energy comes from big wind farms, usually located far from the people who use it. But now, one architect wants to bring wind turbines a lot closer to home. Right in the middle of a busy city, and right onto the very building they will power. The idea is the brainchild of a 37-year-old South African architect named Sean Keeler. Based in Dubai, Keeler has won fame for his skyscrapers all over the Middle East. But for 4 years, he's researched wind turbines, looking for a chance to use them in one of his buildings.
I've become very passionate about sustainable design and incorporating sustainable initiatives within projects that we are designing at the moment.
Buildings consume at least 1/3 of the world's energy. Keeler wants to use green technologies like low-energy cooling systems and super-efficient glass that lets in light while rejecting heat. But he also wants to design a building that will create its own power. An avid sailor, Keeler knows how to read the wind. It is this skill that helps him sense the unique potential of the proposed Bahrain World Trade Center site.
In November 2003, when we first came to Bahrain, there was a tremendous wind blowing. My first impression is I should be sailing. I noticed the wind direction and the velocity of the wind.
Bahrain's capital, Al Manama, sits at the edge of the Persian Gulf. Each morning, as the sun heats the island of Bahrain, hot air rises. This creates an area of low pressure which draws cooler air in from the sea. This daily cycle produces strong onshore winds over 60% of the time. In the heart of the world's biggest oil-producing region, Sean Keeler finds the perfect location for a skyscraper powered by wind. During initial research, he faces the daunting task of figuring out where the wind turbine should go. Rather than just putting them on the roof, Keeler wants to incorporate the turbines into the building. He imagines them on bridges, between 2 towers stacked on top of each other. It's a great idea, but there are 2 major challenges. Turbine blades capture the energy of moving air, sending it to a generator which converts it to electricity. But to be able to rotate, the blades need uninterrupted winds coming directly at them. For this reason, wind turbines are mounted on vertical poles and can turn to face winds from different directions. Keeler's turbines, however, would be on a horizontal axis, fixed in position, unable to turn into the changing winds. The second major challenge is the way Keeler wants to stack the turbines. Because wind speed increases with height, the higher turbine will spin faster and create more power than the lower turbine. All three turbines need to rotate at the same speed, or the top one will wear out sooner. Keeler realizes the key to making the turbines work is the shape of the towers. Again, the architect's experience as a sailor provides the inspiration for the solution. The towers resemble two tall sails. In plan, they have an elliptical shape, like an aeroplane wing. To compensate for the turbine's inability to turn, Keeler hopes the shape and orientation of the towers will funnel the wind directly into the turbine's path. The tapering shape of the towers also means they will funnel more wind to the lower turbine and less wind to the higher one, making all three rotate at roughly the same speed, yielding approximately the same amount of power. It's a brilliant concept, but with no template to follow, the design poses a lot of unprecedented engineering challenges. Keeler needs time to find engineers who can figure out the technical details. However, less than a week after the architect presents the concept, a very enthusiastic client greenlights the project. Bulldozers are instructed to begin clearing the site immediately.
It was a fast-track job of enormous proportions.
With construction underway, Keeler begins searching for turbine manufacturers and bridge engineers. But very soon he discovers others do not share his vision or are daunted by the challenges.
Blade failure resulting in the machine toppling over is pretty rare. It doesn't happen very often at all, but it does happen. And if it were to happen in a situation where there's a bunch of people inside of a commercial building only a few inches away from the spinning blades, the possibility for people getting seriously hurt is very real.
Keeler emails dozens of turbine manufacturers and power providers. They all turn him down. 6 months pass and the Bahrain World Trade Center reaches the 5th floor.
During the research of all the turbine manufacturers that we were consulting, we found that a lot of them were saying, this can't be done. Turbines have always been placed on masts, in greenfield sites, not in an urban environment, and certainly not between two buildings, or on a bridge, where the dynamics of the turbine placed on a bridge compared to if they're on a pole are so different.
As the Bahrain World Trade Center grows skyward with each passing day, Keeler still hasn't found an engineering team to make his green vision a reality. Sean Keeler refuses to give up on his dream of the world's first wind-powered skyscraper. Finally, after 6 months, his persistence pays off. 4,500 kilometers away outside Copenhagen, 2 Danish companies respond to his pleas. Ole Sangil designs turbines. Lars Thorbeck engineers bridges. Normally their paths would never cross, but Sean Keeler wants to put a turbine on a bridge.
And a week later, I flew into Bahrain and I met Lars and Ole. And my first question was, is this really possible? And Lars looked at me and he said, yes, it is. It's taking 2 different pieces of ordinary engineering and just putting it together in a very special way.
So the bridge is stable, even at high wind?
Yeah.
The Danish engineers begin research immediately. They haven't got much time to prove to the world that Sean Keeler's daring vision can be realized.
Yeah, it looks very stable. We have the wing on the backside. I think we should try to turn it just to see it in another direction. Don't you think so?
Yeah. I'll turn it to an angle where it's
First, they need to find out if the proposed wind turbines will produce enough energy to be worth their cost.
So you still expect it would be running at this angle where we are right now?
Yes, I do. Normally, when we have the wind turbine standing out in the field, the rotors will all the time turn in the direction of the wind, following the wind, and in this way create the maximum amount of energy.
But with turbines fixed in place on bridges, the engineers must calculate the wind flow between the towers.
Expect to just see the flow coming through here.
They set up a scale model of the building in the wind tunnel. Dry ice helps them visualize the wind flow patterns, and sensors measure the wind speed between the towers. The tests yield encouraging results.
It's a very nice flow pattern going through directly.
As the wind is forced through the gap between the towers, it accelerates 20%. But the engineers discover something even more surprising.
Yeah, you can easily see the shape of the flow coming through here and changing direction.
We found out that when the wind hit the building, it kind of changed direction when you have a skew wind and make a kind of S shape going through.
The dry ice reveals the towers actually sculpting the airflow, taking winds and funneling them straight onto the blades. The engineers conclude that even winds coming from a 45-degree angle can still turn the blades. They estimate the turbine should be able to produce at least 15% of the building's energy needs. For Sean Keeler, the results are a pleasant surprise and a vindication of his design ideas.
I had some idea at that time that it would work, but I had no idea of how well it would work.
Ola Sangil now knows the turbines will receive a lot of wind. But this also means a lot of stress and fatigue on the materials, what engineers call load. Various locations around the world present different sets of wind patterns. So engineers must adapt a turbine to survive in local conditions. Ola receives 20 years' worth of wind data from Bahrain's airport and uses the information to calculate the winds that will hit the turbine over its lifetime. He simulates 199 wind scenarios, including a hurricane force blowing at 252 kilometers per hour. Ola determines how strong the turbine components need to be. Now he must find a manufacturer, but that might be a problem. The Bahrain World Trade Center requires only 3 generators and 3 sets of blades. For many companies, the order is simply too small. Another hurdle is size. The new trend in wind energy is megawatt blades. This is the largest blade in the world. At 61.5 meters, it dwarfs the 13-meter blades required for Bahrain. The LM glass fiber factory in eastern Denmark produces one of these huge blades every 2 days. A turbine with 3 of these blades will create 5 megawatts of energy a year, enough to power 1,500 homes. This one's destined for a wind farm off the coast of Germany. With market forces biased towards blade volume and size, a unique and technically challenging project like the Bahrain World Trade Center attracts little interest from manufacturers. But the team finds a solution by investigating a pre-existing blade design.
Lars, could you try to move it a little bit up and down to see if it works? Oh, that's great.
With slight modifications, they determine an older model will survive the wind conditions in Bahrain. They also need to enhance the blade's safety features. Unlike other models, the blades in Bahrain will be spinning on an office building above a shopping mall. But the engineers still need to solve the most fundamental design problem: how to put a turbine on a bridge. They use their scale model to study the bridge's performance in various wind conditions. Like the turbines, the bridge must survive exposure to the high winds between the towers. The structure also needs to be strong enough to bear the 11-ton weight of the turbine. But the turbine will not simply be a dead load. The blades will turn up to 38 times per minute, creating a huge moving force on the bridge. For this reason, the engineers discover that the marriage of the turbine to the bridge could create a disaster scenario, a phenomenon known as resonance. The wind will rotate the blades, but it will also cause the bridge to vibrate up and down. If the vibrations of bridge and turbine are ever the same, they will begin to amplify each other, increasing and intensifying until finally the bridge can no longer bear the force. To avoid this catastrophe, the engineers decide to make the bridge design more rigid. This will actually make the bridge vibrate faster than the turbine, eliminating the risk of resonance. But wind tunnel tests reveal another potentially deadly hazard. If the wind changes direction or gusts suddenly, the blades of the turbine could deflect and strike the bridge. A normal wind turbine on a vertical axis is tilted back 5 degrees to avoid the possibility of the blade striking the pole. But that's not an option on the bridge. Each blade is capable of deflecting more than a meter back. To avoid blade strike, the sides of the bridge's front edge are drawn back, creating a slight V shape. The modification creates a distance of 1.7 meters between bridge and blades, enough to avoid a disastrous strike. In theory, the new bridge and turbine design works, but the move to the real world involves many unknowns. With turbine and bridge design complete, the dream of the world's first wind-powered skyscraper is closer to being realized. But there's still a long way to go. On the construction site in Bahrain, senior section manager Simon Hill must keep the project on schedule. The elliptical shape of the towers hasn't made his job easy.
The problem we've got here in terms of the concrete, it's not a square shutter system, it's all curves. So all your shuttering systems are all curved, you're climbing the building up on curves, you've got to set out on curves. It's very difficult to do that. You have to get it right first time. If you start to go wrong, you've got a terrible job to get it back in place.
Although the building presents unique challenges, Hill believes it's all worthwhile.
This is a unique structure. You know, there are a lot of buildings around the world about the same height, but there's nothing to compare to this. There's no other building in the world that's got the features that this has got.
2.5 years after breaking ground, the Bahrain World Trade Center finally reaches its apex of 240 meters. Now the construction crew must tackle their most dangerous task yet, the raising of the bridges. Each weighs 68 tons, and lifting one is an act of absolute precision. The bridges are shaped aerodynamically, like aeroplane wings. Hanging on cables, their sleek shape makes them very difficult to control in high winds. The crane operators lift them slowly, gaining only 11 meters per hour.
Slow the power back down, go to the slower speed. Just a little bit more on the east side, Jack. West side, stop.
Workers only bolt one side of each bridge to the towers. The other end is placed on solid steel rollers. As the wind catches the sail-like shape of these towers, it will make them sway. This, coupled with their expansion and contraction in Bahrain's sun, means the towers will slowly move back and forth. These rollers will allow the towers to move freely, up to 0.5 meter every 10 seconds. But as it goes on, the gap between bridge and tower leaves no room for error.
Up 2 meters
Clearance is just 30 centimeters on one side, 60 centimeters on the other. If bridge and tower collide, the damage could cost hundreds of thousands of dollars.
Jack, we need to come up about 50 mil on the west, so the stumps clear the direction. Yeah, okay.
The third bridge goes on at a dizzying height of 133 meters. Everything is ready for the next phase. The raising of the generators and blades.
So we're going to split into two teams. One team's going to go with Dave to do the turbine, and the other team's going to stay down here to set up the propellers.
We have one plane in that direction, one plane going down there.
Ulla Sangil and Lars Thorbeck fly in from Denmark with their teams. On a construction site of this scale, any delay in schedule means a serious loss of money. So the engineers have been given 7 days to complete the task. There's no time to lose.
Can you get hold of Joseph for me? We may need him to do a bit of translation.
I'm going to get the lads a toolbox talk in a minute.
An advanced crew already installed 2 of the generators. But the top one still needs to be lifted. At 50 kilometers per hour, the wind is too strong to lift anything. But the crew gets it ready in case the wind drops. They raise the 6.5-ton generator slightly off the ground and let it find its balance. The wind still gusts from the southeast. But lift supervisor Dave Root thinks there might be a buffer zone in the shadow of the east tower.
Level 3 straight away, Bago. Level 3. Now. 35 now. Okay, right.
The wind levels off to 35 kilometers per hour. Dave Root decides to go for it. His plan works. The generator goes up quickly, ascending 133 meters in minutes. 18 bolts, 27 millimeters thick, will lock it in place. But first, Dave Root has to reach them. He's harnessed in, but it's still a long way down. He tightens the last one. Despite the high winds, the crew has managed to stay on schedule today. But the sternest challenge remains. All 3 sets of blades must now be assembled, raised and bolted to the generators. Keeler's brilliant idea may unwittingly present the team with their toughest test. Raising aerodynamic blades between 2 towers designed to accelerate wind will be an unprecedented challenge for everyone involved. The following day starts out with a stark reminder of the wind's unpredictability.
We had a storm last night, so I think it just gusted up. The wind speed got up to 110, which we've never heard before, and it blew from the south. Currently we're at 85 wind speed. There's no way we're going to be lifting anything. Forecast is not good.
The engineers have set 21 kilometers per hour as a cut-off point for lifting the blades. Anything higher is unacceptable. With winds howling at 85 kilometers per hour, all they can do is wait. Sean Keeler designed this building to funnel and accelerate wind. At their base, the breadth from one side of the towers to the other is 126 meters. But the wind hitting the building is being squeezed through a gap only 33 meters wide. While all this wind will be good for the turbines once they're mounted, the crew must first deal with the problem of lifting them in such an environment. In addition to wind speed, the engineers also need to consider the wind's direction when they raise the blades.
Because if you have a lot of wind on one side and no wind on the other side, it will be more difficult to control the rotor.
The diameter of the assembled blades measures 29.2 meters. This is just 3.8 meters less than the span between the buildings. A collision would mean a huge loss of money and time. The team assembles the first set of blades and connects them to the central hub. They want to be ready just in case the wind drops to 21 kilometers per hour. Each blade contains 50 layers of fiberglass glued together around balsa wood reinforcements. At 13.4 meters, each one is strong and highly flexible. But each is also aerodynamic, shaped to catch the wind. This will make them very difficult to control as they ascend.
So in principle, we use the ropes to control the movement of the rotor in this direction and in this direction, and also that it doesn't start to tilt.
What you're saying is you want a rope on that blade, a rope on that blade. Okay,
yes,
do no harm, do no harm.
Yeah.
Long ropes will help the ground crew keep the blades from colliding with the building. At 3 p.m., the wind drops. They need 2 hours to complete the lift. If they don't go now, they'll run out of daylight.
We're down to 21. We're up on the bridge now. Norman are up there. They're giving the all clear. So we're taking the load up. It's starting to go up now. So we're ready to go.
One lift hauls a set of 3 blades bolted to the hub, weighing a total of 4.2 tons. At this position, the main tower crane is stretched to its maximum lift capacity. One blade just barely clears the point of the steelwork. At the first generator, Ole Sangil waits and watches. His crew has erected dozens of blades before, but never onto a bridge and never between 2 buildings. The wind remains steady, but changes direction.
We have some gust actually coming from the backside. It will tend to push the rotor out. And we don't want it swinging too much back and forth, so the boys on the ground have to be a little bit alert on that.
If the wind picks up any more, the blades may become impossible to control. The lift would have to be aborted.
If the wind picks up and we have to bring it back down, it's going to be very hard for us to bring it down safely and back down here. We'd have to do it, or we'd park it lower down and wait for another window, but I don't want to be doing that. I don't really want to talk about this, to be honest.
The blades reach 61 meters level with the first bridge. Only 3.8 meters separate blade tip and tower wall. The team must work quickly to dock the blades. There's a problem. They can't get them flush with the generator. The wind from behind forces them back.
We see a stop.
Lift supervisor Dave Root orders the men below to release the guide ropes. They'll try to control it from the bridge.
You just need to follow it. So if I can't hold it for some reason, because we have a gust, then they'll need to take it.
It's docked. They must get a couple of bolts on quickly to secure it.
Thank you. Thank you. Great. First one up.
The first one.
They've made history today. The first turbine ever mounted on a skyscraper. This turbine alone is expected to generate about 400 megawatt hours of electricity a year, enough to power almost 100 average European homes. The wind's energy will hit the aerodynamic blades, forcing them to rotate up to 38 times per minute. The blades will turn a low-speed shaft, which connects to a gearbox. The gears inside will drive another high-speed shaft, spinning it approximately 1,500 times a minute. This will power the generator, producing clean energy for the Bahrain World Trade Center. But there are still 2 more to go. As they go higher, the winds will increase. Even with ropes, controlling the blades as they ascend to the upper bridges will be a battle. On the following morning, conditions deteriorate further. Heavy winds blanket the city of Al Manama with sand and dust. The crew can only assemble the second set of blades. The consistent winds here mean these turbines will be able to produce a lot of energy. But the frequent storms also highlight the risks of having turbines so close to people.
This turbine is sitting in the middle of, we have a shopping mall below it, we have offices on the side of it, and we really need to make sure that we don't have any accidents with it.
These blades have been designed to withstand hurricane-force winds over 252 kilometers per hour. To avoid a catastrophe, the number of safety features on each blade has been doubled. If a blade ever snaps, thick steel cables in the core will hold it together and prevent pieces from flying off. If there's ever a problem, a retractable tip can be released. In the offset position, it will create a huge drag force, stalling the blades in seconds. The second set of blades is ready, but the wind is still too strong. The lift must be postponed. On the following morning, the wind's speed is still too high to lift the blades. But workers can make progress in some of the building's other green technologies. While the turbine will work to generate electricity, the building also incorporates features that will help conserve it.
There's a number of key features which are incorporated into the design, which are more passive orientated in terms of reducing the energy consumed in the building.
To combat the harsh Arabian sun, double-glazed tinted windows will reduce 85% of the heat absorbed into the Bahrain World Trade Center. Efficient air conditioning systems will also slash the high cost of cooling the building in the searing heat. High-efficiency fluorescent lighting on every floor will further reduce energy consumption. Overall, the building should consume half the energy of other skyscrapers in the area. The afternoon brings a brief lull. The crew must seize the hour.
When we get near the top, okay, I don't want the knots going through there. So we pull it, pull it, pull it, and then when we're near...
This time they've learned the lessons of the first lift.
All right, that's on both sides. You understand, yeah?
The wind is from the north. This should push the blades in towards the generator and help the crew get both flush with each other.
Okay, release.
Compared to the first lift, this one goes without a hitch. 2 up, 1 to go. The crew gets closer to its goal. But the final blade will pose the greatest challenge.
Top bridge is the hardest because we have the controlling ropes will have a very steep angle, so we have more difficulty in controlling it.
Simon Hill is also nervous about mounting the blades on the highest bridge.
The top bridge is the big fear for us. That top bridge, the wind is always very strong as you get nearer the top. We've talked about it this morning, and we've looked at the weather forecast. We think we've got a window of opportunity to get bridge 3 up. It's going to be very close.
The conditions need to be perfect.
If we get a gust just as we're about to pin, and it rips the pin out, then you can't control it. You haven't got the strength to control something like that. You have to make sure it's perfect. It's not worth taking a risk.
The Danish team goes to the top bridge to assess the situation. 133 meters above the city of Al Manama, they prepare the generator. The wind measures 25 kilometers per hour, higher than the cut-off speed of 21. It's not perfect, but the forecast isn't good either. If they lose this window, they may have to wait days before they get the chance again. It's a tough call. The lift crew waits for the go-ahead. But the final decision remains with the Danish team.
Wind speed, please. Sign. Ollie wants to stop. Dave, Ollie's got a bit of a concern. He reckons he thinks it's picked up. He said it hasn't. I've just called the driver.
Just keep it on hold for a second. You just want to talk to him and they'll have to find out because they feel like the wind is picking up there.
The wind still measures 25 kilometers per hour, but the Danish team can't decide.
It feels a little bit different from the read between the readings and what we can feel up here.
They need to make a decision soon.
23 north, 23.
Yeah, wind speed's now 23. Well, the question is, at the moment, is it safe to lift at the moment?
No, we are just, we don't want to take a risk. We think it's just on the high side. We don't think they will be able to hold it with a rope from downstairs.
Okay, that's all. We'll drop it back down. We'll take an early lunch and we'll make a decision as soon as we come back.
Okay.
They call it off. When the crew returns, the wind is still at 23 kilometers per hour.
Dave, as soon as you can. As soon as you can, get it over.
Still higher than the cutoff of 21. But if the forecast is correct, this is their last chance for days.
That's a go, is it?
It's 23 up there at the moment. It's very stable. They've gone up to the bridge. They've given us a thumbs up. We're going to start lifting now. They've already gone up to the bridge, so we're ready to go.
When it's out, then...
Take the hook up. Nabby! Take the hook up. Up! Yeah, we had a bit of a coiled up rope problem down here. We're just freeing the rope.
At the worst possible moment, the wind picks up.
Stop the plane. You don't have control or anything.
The Danes stop the lift.
Right, you keep an eye on it, nice and tight, yeah?
The rope handlers struggle to regain control of the blades.
Okay, pull on it, pull on it. You carry on going up, yeah? We're as high as we can on the hooks. We're tight here.
Once they stabilize the blades,
We go up, keep it tight. Keep an eye on it.
the lift resumes. The crane drives the blades in slowly to avoid giving them too much momentum.
We've probably got about another 10-15 metres to go. All we've got to do down here is just keep it nice and tight.
The blades reach 133 meters.
Beauty!
Now the bridge crew takes control. They've got to get it bolted on quickly
Nervous moments.
before the wind picks up any more.
We can't bring it down. Certainly not in a very controlled manner anyway.
Yeah.
It's on.
Fantastic. Okay, let it go. Let it go. That's it. Well done, lads. Thank you.
It was very, very, very pleasing to see that. Just to hear the noise when you can hear the wings hitting the turbine, you can feel it in the bridge.
One more down there.
We're just bringing the ropes down now. Cranes are free to go. We finished down here. So we can put all the gear away, put the men back to work. I'm going to have a cup of tea.
The crane straps drift away. The dream of the world's first wind-powered skyscraper is tantalizingly close. But one final test remains. These turbines still must be turned on to see if Sean Keeler's dream will actually work. Eight months pass and the building nears completion. Systems are now in place that make it possible to operate the turbines. But what's lacking is spinning blades. It's time for the true test. Can the turbines withstand real-life conditions?
It's quite cool, isn't it? Yeah, very good. It's turned out really
Sean Keeler and the Danish team return to validate their years of research and prove the engineering solutions work.
Let's say the first test, and a lot of people around here is very nervous about what can happen because it's very new to them.
There's a lot of work going on at the moment to make sure that everything is ready for the final testing.
Oh, we might be making history here. Yeah. In fact, we are making history.
So today?
But once again, wind conditions must be perfect. If the wind's too low, the turbine will not spin. But if it's too high, testing could be dangerous.
The wind speed is around 8-9 meters per second right now. It's okay for testing.
Finally, the lowest turbine is ready to spin. The Danes release the brake on the turbine. And let the wind take control.
That's beautiful. Absolutely beautiful. I can't believe it's actually going. It's been so long from the first sketch, we're standing here with the turbines going. It's unbelievable.
Once the turbines are fully operational, the blades will turn about 38 rotations per minute.
This is just great. I mean, we have been looking forward to this moment for a very long time.
Over the next 2 months, the higher turbines will come online one at a time. Their performance will be fine-tuned during the first year of operation.
Well done, man. It's fantastic.
The Danish team will monitor the working turbines remotely from Copenhagen.
We did.
These turbines will spin here as a clean energy source, creating around 1,300 megawatt hours of electricity every year. That's the annual equivalent of approximately 2 million tons of coal, or about 6 million barrels of oil. It all began with the vision of one architect.
I'm extremely passionate about pursuing this type of integration into buildings. And I don't want to show that it can only be done once. I want to show that it can be done more and more on many different types of buildings with different solutions.
It's hard to say if wind-powered skyscrapers will become a significant trend. But the team has proven that it's possible.
I'm sure that architects in the future will consider wind turbines as an option, because now it's been done once, so why not do it again?
Perhaps the Bahrain World Trade Center's greatest legacy will be symbolic.
The most important message that the building has is that it is looking at sustainability in a conscious way, but in a very visual way.
Sean, Ola and Lars are already working on another wind-powered skyscraper, this time in neighboring Dubai. In a region synonymous with oil, wind energy has arrived.